Hi everyone. Today we are going to continue talking about lines and planes in space. So we're going to start by creating an equation for a plane, which we have talked about before. There's a standard equation for that. However, this time we're going to do it given 3 points. So hopefully you remember that to make a plane equation, we need 2 things. We need 1 point on the plane, and we need a normal vector. Remember, that's a vector that is perpendicular to the plane. So if we're only given 3 points, we are missing that normal vector. Luckily, we can obtain a normal vector by taking the cross product of 2 vectors that are on the plane. I want to remind you guys that the whole purpose of a cross product is to yield an orthogonal vector. And a vector that's orthogonal, there we go. A vector that's orthogonal to vectors on the plane will be a normal vector. It's going to be perpendicular to the entire plane. So that's how we're going to be using our cross product. Once you have the normal vector, you can pick any of the 3 points and plug those into your standard equation and then put it into general form. For these problems, it's going to be really important that we simplify our general form. So if there is a common multiple, make sure to divide it out. And let's try to also divide out negative so our x value is positive. The reason for this is there's actually many different ways you can approach these problems. You can pick different vectors, you can do different cross products, so your intermediate work might look very different than mine, but you should end up with the same answer. But since there's so many different ways to go about these problems, we want to make sure we simplify so all of our results are the same. Okay, so here let's find the general form of the equation, the plane that passes through these 3 points. So imagine, we have some plane that looks like this. I'm just going to call this point P, point Q, and point R. So let's say it's PQR. So once again, we need to find the normal vector. So we're going to have to take the cross product of 2 vectors that are on the plane. Now, we can use vector PQ, QP, QR, RQ, PR, RQ. You can pick any 2 vectors that you want, and you can take those cross products. So like I said, your intermediate work might look different, but you'll still end up with the same answer. So let's find the component forms of, let's use PQ and PR. So vector PQ is going to be -2, 3, 0, and then vector PR is going to be -4, 0, 3. Sorry, these should be pointy brackets. Okay. So now we have our 2 vectors that are on the plane, and we can use the cross product to find a vector that is orthogonal to both. If a vector is orthogonal to these 2 vectors, it's going to be perpendicular to the plane, which is what we want. So I'm going to call that normal vector n. So that normal vector is just going to be the cross product of PQ and PR. So let's find that normal vector. So n, let's set up our 3 by 3 matrix, and we're going to find the determinant. So I'll use the diagonal method here. Okay. So n is going to be 9i plus 0j plus 0k minus -12k plus 0i minus 6k. So our normal vector will be 9i plus 6j plus 12k. Now this is just one of the normal vectors. There are actually an infinite number of vectors that are perpendicular to this plane. So if you would like, you can kind of simplify this expression. You can divide them all by 3. What you'll end up is a scalar multiple, and if something is parallel to a perpendicular line, it is also going to be perpendicular. So you can use this or a different form of that. So now that we have our normal vector, these can be our A, B, and C values, and you can pick any of the original 3 points. I'll pick point P to use as your x1, y1, z values. And just a quick recap. this is what the standard equation looks like. So all we have to do from here is substitute our values. So we have 9 times x minus 2 plus 6 times y minus 1 plus 12 times z minus 1 equals 0. So now we're going to put it into general form. And if you distribute and combine like terms, you should get minus 36 here. And now this is technically a plane that contains those 3 points, but let's simplify this general form by dividing out a common multiple of 3. The reason why, again, we're doing this is because there's essentially an infinite number of ways you can approach this problem depending on which vectors you decided to use initially, depending on what order you decided to take the cross product, depending on what form of your normal vector you decide to use. Your intermediate work might look very, very different, but if you do it correctly and you simplify completely, you should end up with this same result. So this is the equation of our plane. Just to recap, to make an equation of a plane, you need a point and a normal vector. We had to find our own normal vector by taking the cross product of 2 of the vectors on the plane. From there, it's just using our standard form and plugging in the values. And here it was that standard form. Okay, go ahead and pause the video and give this one a try. All right, so remember, perhaps you chose to make a different pair of vectors, or you did the cross product in a different order. But essentially, here's the normal vector that I got, and I chose to use this coordinate. I plugged it in, and I got an equation that looked like this. So then I simplified it, and you should end up with 3x plus y plus 2z minus 13 equals 0. All right, so now we're going to talk about finding the angle between 2 planes. So actually, to find the angle between 2 planes, we're not going to use the planes themselves. We're actually going to use their normal vectors, because the angle between the normal vectors should equal the angle between the planes because they maintain the same relationship to each other. So this is a formula that we have already talked about to find the angle between 2 vectors. So we're going to use n1 and n2 as normal vectors to our 2 intersecting planes. So the cosine of that angle is going to be the absolute value of the cross product of the 2 vectors divided by the respective magnitudes of the 2 vectors multiplied. So like I said, we've done this before. A few things we can conclude. If our cross product is 0, our angle must be 90 because the cosine of 90 is 0. In fact, that's how we test for orthogonal vectors. We check to see if the cross product is 0. Another thing to note is if your normal vectors are scalar multiples, that means your normal vectors are parallel, which means the planes are also parallel. All right, so let's give this one a try. First, we are asked to find the angle between these 2 planes, and then we're actually going to find the parametric equations of the line of intersection between the 2 planes. So when 2 planes intersect, it will always create a line. So let's start by finding the angles. The first thing we're going to need to find are the normal vectors. So the normal vectors are super easy to find. You essentially just take the coefficients of x, y, and z. The reason for that is if you look back at our formula, which looks like this, here are the values from our normal vector, a, b, and c. When you distribute those values out, a is always going to be the coefficient of x, b is the coefficient of y, and c is the coefficient of z. So it's super easy to find those normal vectors. So a normal vector to that first plane will be 1, -2, 1. And a normal vector to the second plane will be 2, 3, -2. So we can find the angle between these 2 normal vectors, which will also be the angle between the 2 intersecting planes. So let's start by setting up our formula. The cosine of theta is going to be the absolute value of the cross product. So we do 1 times 2 plus -2 times 3 plus 1 times -2, which is -6. So the absolute value of -6 over their magnitudes. So here we have the square root of 1 squared plus 2 squared plus 1 squared, which is the square root of 6. Oops. So that's the magnitude of n1 equals the square root of 6. Let's find the magnitude of n2, square root of 2 squared plus 3 squared plus 2 squared, which will be the square root of 17. So we do the square root of 6 times the square root of 17. So we end up with cosine of theta is positive 6 over the square root of 102. And now this is clearly not a unit circle angle, so we're going to have to use arc cosine to find a decimal approximation. And we should end up with approximately 53.55 degrees. So now we're going to find the parametric equations of their line of intersection. So for this, remember the parametric equations will look something like this. And something really nice about this problem, if you look at these two planes, we can conclude that they are going to intersect at the point 0, 0, 0. This is a value that works for both, and the reason for that is that there's no constant here, which means that we can use this as our x1, y1, z1, which means that we essentially don't even need to worry about those. Our equation will just look something like this. So remember, we are going to want to define x, y, and z in terms of some parameter, which we'll call t. Well, luckily, this is exactly what will happen because we're solving a system of 3 variables with only 2 equations. So we will have to find some way to define each variable in terms of something else. That's the only way to solve this type of system. So I'm going to start by using the elimination method. I'm going to multiply that top equation by -2 so I can eliminate my x terms. So we have -2x plus 4y minus 2z equals 0, and then our second equation will remain the same, and we end up with 7y minus 4z equals 0. From here, I can solve for either y or z. Let's solve for y. So it's going to be 4z over 7. So now I'm going to take that and I can substitute this into either of my original equations. Let's substitute it into that first equation. I'll zoom back in a second. So we're going to substitute into equation 1. So x minus 2 times y, which we're going to replace with 4z over 7. There we go. Plus z equals 0. And here we're going to, let's solve for x. So here we have x minus 8z over 7 plus 7z over 7 equals 0. So that gives us negative z over 7. So x equals positive z over 7. So now we have y in terms of z, we have x in terms of z. Now we need to pick one of our variables and set it equal to our parameter. So let's say let x equal t. So that's going to be actually our first parametric equation. X is equal to t. Now if x is equal to t and I substitute that right here, we can solve for z, and we can say that z is equal to 7t. Once again, I let x equal t and I multiply both sides by 7. If z equals 7t, I can substitute that right here. My 7s will cancel out and I'm left with y equals 4t. And this is actually my set of parametric equations. Remember, we can use that point 0, 0, 0, so x1, y1, and z1 are all 0. So all we had to essentially figure out is what those a, b, and c values are. And that's exactly what we did. So this can be a little bit tricky, but just remember, we have solved systems of equations like this. You just do your best to isolate, and eventually you have to pick one of your variables and set it equal to t, and then put everything in terms of that new parameter. Okay, go ahead and pause the video and give this one a try. Okay, so let's start with the angle. Here our cross product is actually 0, so the angle between them must be 90. Then I went through the process of solving my system. So first I eliminated my x's, I solved for y. I substituted that into my first equation right here, and I solved for x. From here I decided to let x equal t, and that means that z is equal to negative 2t, and if you substitute that here, that means that y is equal to 4t. So this is the set of our parametric equations, because once again, x1, y1, z1 is 0, 0, 0. We know that that's a point that works for both planes. All right, so now we're going to talk about sketching planes in space. So essentially what we're going to want to do is we're going to want to find our x, y, and z intercepts. So you can do that in a few different ways. We have talked about how to make x, y, or y, z, or x, z traces of your plane. Remember, that's just the shape that takes place when a plane intersects one of your original axis planes. So you can find the xy plane by setting z equal to 0. So when you do that, you essentially have a two-dimensional linear equation. From there, you can set other values equal to 0 to find the intercepts. So essentially, once again, we want to find the x, y, and z intercepts. Then you plot those points and connect them to form a triangular plane, and then you just shade it in. A few things to point out. If one variable is missing, that means your plane is not going to hit that axis, which means that it's parallel to that axis. If two variables are missing, then your plane will not hit either of those axes, so your plane is actually parallel to one of your coordinate planes. So just be aware that that can happen. All right, so let's give this first problem a try. Just for practice, let's find the xy trace of this plane. So remember, we find the xy trace by setting z equal to 0. So if I set z equal to 0, we have 3x plus 2y equals 12. This is just a linear equation in the xy axis. So you could graph it. We could also really easily find the y-intercept by setting or we can find the x-intercept by setting y equal to 0, or we can find the y-intercept by setting x equal to 0. So here we would know that x is 4 and that y is 6. So this gives us the coordinate 4, 0, 0. Remember, we already set z equal to 0, and 0, 6, 0. And we are still missing our z-intercept, so we can find that by setting x and y equal to 0. 2 times 0 plus 4z equals 12, so z equals 3, which gives us the coordinate 0, 0, 3. So now we know the three intersections. Now we just have to plot them and connect our dots. So remember, this is our y-axis, this is the z-axis, and our x-axis looks something like this. Okay, so positive 4, 0, 0 is going to be somewhere on our x-axis, 0, 6, 0 is going to be somewhere over here, and 0, 0, 3 is somewhere right here. And you connect your dots, and this is our plane. So you can shade it in to show it. There you have it. Okay, so now the last thing we're going to talk about is how to find the distance between a point and a plane. So let's assume that point Q is some point that's not on your plane. The distance between that point and your plane, well, of course, the distance, we're going to want to find that perpendicular distance to your plane. Okay, however, we might not always know what the value is that is perpendicular to that point. So let's just say that point P is just any point on the plane, and then N is a normal vector to the plane. Oops, let me add in the word vector. There we go. So the formula for that distance is the dot product of vector PQ. Remember, P is some point and Q is the point off the plane, and that normal vector, and then you're going to divide it by the magnitude of that normal vector. So essentially what's happening is we're actually doing a projection of PQ onto N, and that will allow us to find that perpendicular distance. Okay, so let's see if we can find the distance between point Q, which is 1, 5, negative 4, and the plane 3x minus y plus 2z equals 6. So we're going to need two things. We're going to need to find some point on our plane, and we're going to need to find the normal vector. So our normal vector is very easy to find. Remember, it's just the coefficients of x, y, and z. So we can say 3, -1, and 2. And now we just need to find some point that is on our plane. So we can do this by essentially setting other values equal to 0. So to find a point P, let's set y equal to 0 and z equal to 0. And let's see if it actually crosses our x-axis somewhere. So if we set y and z equal to 0, we have 3x equals 6, so x equals 2, which gives us the point 2, 0, 0. Now you could have set x and z equal to 0 or y and z equal to 0. I just chose to find an x-intercept. So if we know that P is a point on the line and that Q is a point off the plane, or sorry, P is a point on the plane, Q is a point off the plane, we do need to find that PQ vector. So we can just do a quick component form. 1 minus 2 is -1, 5 minus 0 is 5, and then -4. So we have PQ, and we have N. Those were the two things that we needed for our formula, our normal vector and the vector of a point to a point off the plane. We will also need the magnitude of N for our formula. So the magnitude of N is going to be the square root of 3 squared plus 1 squared plus 2 squared, which is the square root of 14. And now we just plug those values into our formula. So the distance is going to be the absolute value of the cross product of N, or PQ, and N. So we have -1 times 3 plus 5 times -1 plus -4 times 2, which gives us -16. And then over square root of 14, and that will just give us +16 over the square root of 14. So that is the distance between point Q and our plane. Now, of course, you could plug this into your calculator to get a decimal approximation for this as well. All right, so go ahead and pause the video and see if you can give this problem a try. All right, let's check our work. So here you can see that a normal vector could be 2, 5, -1. Here, just to make it a little bit easier for us, I chose to set x and y equal to 0, and because I noticed it'd be easiest to solve for z. So we know that one point on the plane is 0, 0, -3. So then I created the component form of vector PQ from the plane to the point that's off the plane, and this is the component form of the vector. So if I take the cross product of PQ and N, we got -6. If you find the magnitude of vector N, you get square root of 30. So our distance is just 6 over square root of 30. Okay, that is all for today's lesson. Thank you so much for watching.